Hello everyone, my name is Mahadi Hassan and I am doing my PhD in the University of Texas at El Paso, which is also known as UTEP. In this video, I will be describing my project that I have done in my computational mechanics course, and my project title name is High Pressure Experimental Boiling Test Facility. The following outline will be covered in this video. So my slides are containing these outlines, the motivation of my research work, the background and the similar kind of projects that I have done before, the objectives of my research work, the geometry that I have done for my research, the boundary conditions, mesh optimization, simulations, discussion, and conclusions. For the motivation of my research work, as I am highly interested in the heat transfer mechanism, boiling, and nuclear reaction stuffs, these things actually motivated me for doing my research in pool boiling facilities. So, pool boiling is an efficient but very complex mode of phase change heat transfer, including hydrodynamic instabilities, heat and mass transfer, and surface sciences. Boiling heat transfer is used in a number of industries and plays a critical role in various large-scale applications, mainly in the nuclear reactors, as inside hundreds of tube bundles there are going chain reactions of fission at high pressure and tremendous temperature. So whenever the energy is generated, also a tremendous heat is generated, and to cool down these control rods, water is circulated, and for cooling down those rods, actually water is circulated, and pool boiling is occurs or boiling is occurs on the surface, on the outer surface of those rods. But because of the flowing fluids, we cannot see the boiling phenomena by bare eyes. So the boiling phenomena is there. So if we can enhance these boiling phenomena, or pool boiling enhancement was done, then the efficiency of the cycle can be improved. So from these facts, I got the motivation, and our research is going on this topic. Talking about the enhancing in the pool boiling facilities, it can be done by enhancing the surface properties, also by incorporating the micro nanostructures onto the surface. Also, we can enhance pool boiling by changing the fluid property or by using different types of fluid. More recently, there are works have been going on for making this pool boiling performance better by increasing the heat transfer coefficient and making the range or increasing the range of critical heat flux higher and higher. So by doing these steps, we can enhance the cycle efficiency and also the power generation. So for the background, I will say that for the enhancement in pool boiling facilities, lots of research has been done, and lots of research are going on. Maximum of the researches are mainly over flat surfaces or enhanced surfaces with micro nanostructures, but mostly the researches are operating at atmospheric pressure. But if anybody relates his research work or her research work with the nuclear reactor facilities, then the operating pressure should be much higher, because nuclear reactors are working at 160 bar pressure. So there are lots of limitations then for which we cannot going these operating pressure higher, but few of the researches are going on with different fluid and fluid properties operating with different pressure, but not exceeding 10 bar. Talking about the similar kind of projects, this I cited this project and research work which has the title of Full Boiling Heat Transfer Performance of a Dielectric Fluid with Low Global Warming Potential. In this article, we can see the experimental data and which compares various correlations for predicting the pool boiling heat transfer coefficient of a new low GWP fluid FK649. Using a pressurized boiling facilities with a smooth aluminum heater, the critical heat flux and heat transfer coefficient were measured for the pool boiling of FK649 at various saturation conditions, where the operating pressure was up to 6.7 bar. So here it's also seen that the operating pressure is limited and it is less than 10 bar. So my thinking was that if we increase our operating pressure, like starting from the 10 bar pressure and facilitate the things and see the tube structures and see the boiling happening on the surface, and if we can manage to enhance those properties and enhance the boiling facilities, we can contribute a lot, a huge thing in the nuclear reactor sites. So for this we need to design our experimental setup which can withstand high pressure like up to 20 bar and high temperature. So for that we need to analyze which material is suitable for us. So here in this I will analyze 304 stainless steel and also 316 stainless steel for our cube block, and I will compare these two materials and we'll see what is happening. Besides, to analyze also for our experimental setup, there will be two window sections, and the window section will be transparent, and we are using quartz glass for that window. So the quartz glass thickness is also important. So I will be also analyze the quartz glass thickness for the window section which can withstand the operating high pressure. Besides, our as per our design, the as per our design, there are four columns which will stand or which will contain the whole weight of the system. So I also want to observe the column loads on the four rods of the experimental setup. For the geometry, as it can be seen here in the slide, that at the very left side of the slide, there is a complete 3D design of experimental setup, and right next to it is the 3D design of cube block and column structure. Right next to is the 3D design of cube block, and the very right of the slide, we can see the 3D design of column structure. In this slide, we can see the 2D view and the detailed dimensions for the cube block and the rod column dimension. This slide is describing and showing the glass thickness dimension that is done in the ANSYS design modeler, and also the bottom and top block dimensions. So for the designing the geometry of our experimental setup, some parts of the geometry was done in the SolidWorks software because the design was really complex, and after designing in the SolidWorks, the folder was incorporated in Design Modeler by converting the .slr ASM file into .igs file. The cube block and the rod column structure are mainly drawn in the Design Modeler, and in the XY plane. Besides, different planes were used to draw glass geometry and top-bottom shape. This one is very important, the boundary conditions. As we know, the operating pressure and temperature in nuclear reactors is about 160 bar and 180 degrees C, respectively, but there are some limitations and safety issues, so we cannot go that much higher pressure in our lab facilities. So we are thinking about starting with 10 bar pressures, and for safety factor of design and avoiding any casualties, we will be incorporating the pressure up to 20 bar in the cube block, and if it is safe enough to use, we will use that. Besides, for the column load, the total weight of the setup is taken as 700 Newton, which is more than the actual one, and was applied each of the column loads to analyze the deformation. If the columns collapse, new rod column will be designed and introduced which can withstand the load. So in this slide you can see that fixed support is induced at the bottom plate of the cube block, and the figure is upside down as you see the top side, the bottom plate. Also, frictionless support is induced as there will be metal gasket in between the in between the side blocks and the glasses, and thus the frictionless support is induced. So the main boundary conditions for pressure is here. As we can see that 20 bar 2 megapascal pressure is induced from all direction inside the cube block, and all the faces were selected sequentially. I just hided the bottom part of this block to see the selected items inside the block. So thermal condition was also induced here, and a temperature of 180 degree is incorporated to the entire cube block for analyzing the thermal strain. For the rod column structure, a fixed support is induced as well, where the four legs of the rod structure is selected as fixed face body. 700 Newton force is applied at the four corners of the rod structure, which indicates the total weight of the setup. For the mesh analysis, in this slide we can see that for meshing the relevance was 100, and for the sizing the relevance center was fine, element size was 5 mm, initial size seed was active assembly, smoothing was medium, transition was fast, span angle center was coarse, and the minimum edge length was by default 4.4450 mm. After generating the meshes, the statistics shows that the number of nodes were 117876 and the number of elements were 54,890. This slide is describing the mesh analysis and the mesh controls in detailed form. This is the mesh analysis for the rod column structure, where the relevance is 0. For the sizing, the relevance center is medium, element size is in default, initial size seed active assembly, smoothing is medium, transition was first, span angle center is coarse, and minimum edge length is by default. After generating the mesh from the statistics, we can see that the meshing contained 330732 numbers of nodes
and 173941 numbers of elements. For the results sections, actually I was trying to hit two birds with one pile. So here I was doing both the optimizations for the quad glass thickness and also the comparison between those cube blocks of different materials where I using 304 stainless steel and 316 stainless steel. So for the engineering data, I incorporated the properties for 304 stainless steel and 316 stainless steel individually and ran through the simulations. And for this, we are having the total deformations for whenever the quad glass thickness was zero point 0.6 inch. For 304 stainless steel, the total deformation value is maximum of 14.47 millimeter, and for the same design, the total deformation for 316 stainless steel cube block is 14.46 millimeter. So by comparing these two datas, we can conclude that the 304 stainless steel and 316 stainless steel are pretty much similar and they differ not very much. Shear stresses onto the block was also observed, as we can see that for the quartz glass thickness 0.6 inch for 304 stainless steel, the shear stress value is 1618.2 megapascal, and for the 316 stainless steel, the shear stress maximum has the value of 1657.2 megapascal. So it didn't differ much here also. We also done the thermal strain thing. So for both of the cube block for 304 stainless steel and 316 stainless steel, the thermal strain is low and it's the maximum thermal strain is 0 millimeter per millimeter here. So the design is quite good for this. As I was talking about the optimization of the glass thickness for quartz glass thickness 0.8 inch, I also ran through the simulations and got the data for total deformations for both of the cube block. So whenever it was 304 stainless steel, the deformation for this maximum is 11.8 millimeter, and for 316 stainless steel, the total deformation value maximum is 11.79 millimeter. So here it is also not differ much. Also for the shear stress solutions and also for the thermal strain. Here in the slide we can see the verification of loads on rod column. So as per our incorporated force on the four columns of the rods, we we induce 700 Newton each on those rods and see the deformation. So the total deformations value are showing here is maximum 0.003 millimeters, which is very low in small in scale. So it can be said that the structure will not collapse. The directional deformation was also done, and it's seen that in the y direction the directional deformation is less and it's the maximum deformation is 0. By seeing the equivalent stress von Mises stresses solution, it's seen that the maximum stress has developed in the scale of 8.18 megapascal, which is very below than the tensile strength of the rod material. So here for the rod materials we are using high strength rod stainless steel rods. So for this tensile strength and the properties of this rod, it will withstand this stress. For the equivalent elastic strain solution, it's seen that the values are very negligible. For the analysis and discussion part, I would like to start from the comparison between 304 stainless steel and 316 stainless steel cube block. As I was designing the things in ANSYS and in Design Modular, in ANSYS we can incorporate the engineering data. So whenever I was using the datas, I I collect the datas from a very renowned site and very reliable site. So for 304 stainless steel, I use the properties of modulus of elasticity of 190 gigapascal, Poisson's ratio of 0.265, density of 8,000 kg per meter cube, tensile ultimate strength of 505 megapascal, tensile yield strength of 215 megapascal. And for 316 stainless steel, I was using modulus of elasticity of 193 gigapascal, Poisson's ratio of 0.265, density of 8,000 kg per meter cube, tensile ultimate strength of 580 megapascal, tensile yield strength of 290 megapascal. From the static structural analysis, it is seen that for the same design and dimensions, both 304 stainless steel and 316 stainless steel showed similar kind of solutions, and thus we can use both of them, which can withstand the operating pressure and temperature. Besides, by varying the glass thickness, different solutions were achieved for optimizing the glass thickness. Though thermal strain and shear stress solutions were satisfactory, but the total deformation in the glass area can be seen from the analysis. The maximum deformation can be reduced from 14 mm to 11 mm by increasing the thickness from 0.6 inch to 0.8 inch, and thus 1 inch glass thickness will be used, which will be much safer. Besides, similar kind of work is found where they use quartz glass thickness 1 inch as well for their experimental setup, and they are having those window selection as well, and they were operating their experiment at 6.7 bar, but it can withstand up to 15 bar. So pretty much from the reference of their work, we are going with this. So here is the results for the quartz glass thickness when it was 1 inch. So we can have the total deformation, equivalent von Mises stress, thermal strain, maximum principal stress, and also maximum principal strain. So these results were not that much converse and actually is below the safety mark. As we are using for high strength steel rods as the columns of our experimental setup, it is important to verify the loads on it, and it should also be observed that it collapses or not. Thus, for rods of 16 inches each at the four corners of the setup were set at, and 700 Newton loads were given onto the rods to verify its ability. The system's weight is taken as 700 Newton approximately, as the exact value of the total weight of the system is below that, and by running the simulation it's seen that the system is not failing at the operating conditions. This slide is talking about the material data that was incorporated in the engineering data of ANSYS. So here you can see the structural steel and high strength steel datas. Here you can find the 304 SS datas and quartz glass datas. For the conclusion part, I want to say that actually I obtained the objectives that I want to obtain by this work, as the simulation data for 304 stainless steel and 316 stainless steel on the Q block did not differ much, and thus 304 stainless steel can be used instead of 316 SS withstanding the required pressure and temperature. Besides, 304 stainless steel sheet is more available and can be machined easily because 304 stainless steel is much softer than 316 stainless steel. So for our minimum operating pressure of 10 bar, we are hoping that we will be using 304 stainless steel for this Q block geometry. As per the optimization of glass thickness, we actually are going for 1-inch thickness for the experimental setup of window section, as we found the similar kind of research work which can withstand up to 15 bar. The total weight was considered as 700 Newton, which is actually higher than the exact one, and by applying these loads onto the four columns, it can be seen that the deformation was a very small scale of 0.004 inch, and thus the structure will not collapse. At the very end, for the acknowledgement, I am really helpful and grateful to Dr. Stewart, who actually conduct this course, and I learned a lot of things by taking this course, and really he is a very good friendly teacher, and he really taught us very well about the simulations and the software thing of ANSYS, and thus we can design and simulate many things in static structures, also in transient things, the explicit things. So really, I'm really grateful and really learned a lot from this course. So that's all. Thank you, everyone.